So when people ask me what I do, and I say I work in fashion, people often say, oh, with models. And I often say, yes. But of course, I'm talking about statistical models rather than the human variety. So anyone who doesn't know who List are, we basically sell clothes. But the difference for us is that we collect all our information about clothes dynamically from the web. So if you think of it in terms of data science, our main goal is to take this stream of inconsistent, semi-structured fashion data and transform it into a consistent catalog for our users, and then our users can buy stuff from us. So basically, the way List makes money is by transforming data into this consistent thing that we can present. So fashion. It's an interesting business to be working in, particularly because fashion is a visual medium. So a lot of things that users are interested in aren't captured by text or descriptions of products. Like, I think you'd be very hard-pressed to describe these products and do them justice, for instance. You really need the visuals to appreciate the outfits fully. So it makes sense for us when we're doing things like search, or we're doing recommendations, or we're doing duplicated product detection or trends forecasting, anything like that. We should have visual features in our machine learning models. Okay, so today I'm going to talk about this. Can we build a general purpose fashion model that we can feed into all of our data science processes and machine learning models at List? So the way that we can achieve that is through deep learning. I'm not going to go into too much details about deep learning in this presentation, but I want to talk about two aspects that, for me, where all the benefits come of using deep models. So compositions. There's like two things to think about in terms of composition. There's like the architecture that you're specifying, and there's like parameters. So I'll talk a little bit about the parameters. Obviously, one reason we use deep learning is because it's accurate and it gives us high, good performance. And the reason for that is the relationship between the degrees of freedom of the decision boundary in a deep model and the number of parameters is exponential because we're stacking parameters up above each other. So one set of parameters influences the next, that influences the next. So you get this hierarchical effect of the parameters. Whereas you think of a more classical model like regression or a random forest, then there's almost a linear relationship between the number of parameters you have and your discriminative power. So that's one thing about deep learning, that we get a lot of power from a relatively small number of parameters. But the bit that I really like is this architectural composition. So I like to think of it with a traditional model. If you want to do something very bespoke and particular to your problem, you have to be a carpenter. You have to derive lots of things from scratch, do lots of research. With deep learning, if you want to do something very bespoke and specific to your problem, it's a lot more like Lego or IKEA, for example. You just take a lot of components that exist in the ecosystem and you can slot them together to create something really bespoke for your problem. I'm going to go into this a bit later when I talk about our model. Okay, the other thing is representations. This is probably one of the most powerful things about deep learning, although representations aren't necessarily only for deep learning. You can have these non-deep representations, like word2vec is an example. That's a non-deep representation. Or even like classical image processing has a lot of sort of key point descriptors and various vectors that could be considered representations as well. But why representation is important? Well, I want to do this quote from Bengio in his 2004 paper. So AI must fundamentally understand the world around us, and this can only be achieved if it can learn to identify and disentangle the underlying explanatory factors hidden in the observed milieu of low-level sensory data. That's a very academic sentence, but I think it gets to the heart of the matter around representations. So essentially, models need more than simple point-wise symbolic concepts. So I'll show you an example. They need like deep context around the things they're modeling. So I'll show you a good example. So here's some concepts that I presume we're all familiar with. Cat and dog, which are animals. Female and male, which are genders. And I don't think anyone would argue if I said, cats are quite close to dogs, and females are quite close to males, if you think of the semantics of those terms. They're very, very close. So this is the audience participation section of the presentation. So if we take cat, would you say cat is closer to female or closer to male in terms of the semantics? What would you say the concept of cat is closer to, male or female? It's like, okay, who votes male? Okay, who votes female? Okay, good. Good. You haven't ruined the presentation. Likewise, dog, closer to female, closer to male. Yeah, good. Thank you. Good audience. So that is really interesting, I think, because if you take this traditional view on AI, say the symbolic approach, where if we were modeling text and we wanted to represent a cat to our model, we'd probably do something like a one-hot encoded vector, which is a point-wise estimate. It has no context around it. It's just a symbol. It's just a one. Like, this is a cat, and we know nothing else about cats. Likewise with dogs or females or males, it'd all be these point-wise estimates, point-wise encodings. So why do humans think that cats are close to female and dogs are close to male? Because you have this rich context surrounding these symbols, this rich semantic context that underlies the surface symbol. And that's what we need to put in the models as well. The models need to understand that cats and dogs are similar, males and females are similar, and so forth. And that's where representations come in. So instead of just using one-hot encoded symbols, we use vectors, which we call the representation. That vector somehow encapsulates knowledge about that symbol that we're interested in. So again, I'll show you some examples later. Okay, so the model. So this is our data at list, typical data. We have a product, an Acne jacket, and we have 3 different images of that jacket from 3 different retailers. And as you can see, they're different lighting, different models, different angle, different saturation, all those things. And we can also have multiple images from one retailer, typically it would be the rotation of the product, right? Or different angles of a shoe or something like that. So first thing about our products, we have multiple images. The second thing about our products is that we have multiple labels. So you can see an example here. So we know that the product's for men, we know its color, we know the jacket's slightly shiny, it's got a zip, and we know it's a jacket. So we have all these various labels that we can attribute to our products. So when we train this visual model and get our representation, the model should be able to take multiple images for each observation. And it should be able to optimize that representation based on multiple labels. That way we're making use of all our data and all our knowledge about fashion. So this is sorry, you probably can't see this well. I've got a zoomed in one coming up. But this is the rough architecture, very high-level architecture of the model that we've designed. I just quickly go through it at a high level. All we do is images go in at the top. The images go through a bunch of convolutional layers. And the architecture we're using for convolution is something called ZFnet. ZFnet is a slightly better version of architecture called AlexNet. And AlexNet is the architecture that sort of came onto the scene and blew traditional image processing away and won all the competitions. So this is a slightly improved version. But this is actually quite an old architecture. There are even new, fancier ones, but they're very computationally expensive. You need multiple GPUs, and they're hard to use on production and that sort of thing. So we're going with a simple one that just works. So. And this can also easily run on multiple GPUs if we want to speed up fitting. We use something called data parallelism, where we take our training batch, split it into n chunks for n GPUs, give each GPU a chunk, and then do the forward pass, and then get the representation at the end and consolidate it all. So you can speed it up that way if you want. And by the way, this is all done in Chainer, which is a Python library that basically has its own CUDA bindings for the GPU. And it's very easy to use, it's good at multiple GPUs, and its error messages are really easy to understand. So I don't know if anyone's got experience with Theano. That's probably the opposite in Theano. But it's a bit slower than Theano, so it doesn't do graph optimization or anything. OK, so let's zoom in a bit. So if you remember, our two things we wanted to achieve is multiple images per input and multiple labels. How can we do that in a deep network? Well, the multiple labels is actually incredibly easy to do in a neural network. All we do is we calculate multiple losses at the end of the network. So in a classical model, your loss might be, mean squared error or softmax cross entropy or something like that, where you're saying, how well is my model currently predicting my labels? And it gives you a number. In this case, if we have 5 sets of labels or 10 sets of labels, we just have 10 losses. So we have 10 different numbers that say, how well is the model doing against our 10 labels? And to consolidate that all and update our parameters, we simply take the mean of all the losses and backprop that. So we're just taking the mean of all the tasks and putting that back through the network. You can do it in fancier ways. So you can just sum them together and weight them if you think one task is more important than the other or whatever you want to do. But all the tasks are important for our representation, so we're just taking the mean. The other bit, which is slightly trickier, is how do we put multiple images into our deep model and get a single prediction for them and a single representation. So what we actually do is when we're creating batches for our model, we group images together so that every product in a batch has the same number of images. So say we have a batch of 2,000 products we're training on. Every product in that batch will have, say, 5 images. So they all have a consistent amount of images. Then we take our convolutional part of our neural network and duplicate it 5 times, one for each image. We put them through the 5 copies of the network simultaneously. And at the end, we'll have 5 representations coming out for each image. To combine them, we simply take these 5 representations, which are vectors, stack them into a matrix, and do column average pooling across all columns. And we get back to a vector, but the vector is now basically column-wise mean of every single image representation. You can also do max. Max is an option as well. And the idea is, say, the first column of our representation represents, I don't know, how red a product is. I mean, it wouldn't be this obvious, but say it does. Then if we use something like max pooling, we're saying, if any image contains something red, our final representation should say something is red. That would be max because we're taking the highest activation from the column. Whereas mean is sort of the average. It takes the average of all the activations, so it's a different way to do it. The reason I did average is that we found we got better results on color, on the color task, predicting the color of a product when we're doing average pooling over max. So that's that. And then so it's actually quite easy to do these 2 things. It's not too tricky. We've just combined a bunch of components, stuck them all together, and then now we can do multitask and multi-image learning. If you think, how would you do this with a random forest or a SVM or logistic regression, right? It would be much, much harder, I think, to try and do this. So some details on training. We trained for about 20 epochs on a GPU. It's about 5 hours a epoch, and that's actually quite fast for some of these models. The more modern ones literally take days. And there's about 16 million parameters. So if you think of a regression problem, we've got 60 million coefficients, basically. Impossible to look at them and try and figure anything out. And it's trained on about 4 million images. So we train that for a few days, and then we can test it out with something like this. So we put in a pair of blue. This is a very easy example. It's very clean. It's very blue. If there are more complicated ones that don't work quite as well. But so we put these 3 images in, get our representation, and run predictions on a representation. You see it gets it right. So blue, it's for men, it's a shoe, it's a sneaker, it's a low top. So that's good. Not always as good, but it's good. And then overall, we get about 80% accuracy on all our images, with the lowest accuracy being subcategory, which is quite hard to predict because it's things like maxi dress versus cocktail dress versus evening gown, and they all look the same to me, so I don't know. The fashion people come up with them. And also color, and the reason that color is so low, only 73%, is just because color is really ambiguous, even for a human. So you can see when our humans make decisions, when does beige become white? When does beige become brown? When does very pale green become gray? When does pale blue become gray? And there's all these decisions. Basically, each of our human moderators has a different way of doing it. So there's some inconsistencies. And sometimes products have multiple colors, like black and white, and they'll only be tagged with one color. And our model thinks it's white, but our moderator thinks it's black. So, I mean, it is right, but not according to our labels. So I'm going to show you something later that shows how these inconsistencies arise. So internals. So we've trained it. Let's have a little look inside. So here's a nice image. So what we did here is took maybe 50,000 products the model had never seen before, so it wasn't part of training. Calculate representations for every model using all the images. Again, the representation is just a big vector. Then we project this vector down into 2 dimensions using Tesny, and then plot those on a plane. So essentially, things that are near each other should be similar to each other semantically. And you can see it works quite well with this little island. They're all handbags. They've all got a handle that's up. So it looks like, if you think some of our tasks are about shape, and it seems like the representation is understanding shape. It's grouping things together. You can see in the top corner as well, there's a little belt island. So it seems to be grouping shapes well. That's good. One of our other tasks is color. And it seems to understand color as well, as we have sort of like a rainbow of bags going across. So it seems to understand how to group colors together as well. So this is like a nice debugging method just to make sure you're not doing anything crazy. OK, here's another one. So the nice thing about convnets, the first layer of a convnet, is that images have 3 channels, red, green, blue. So your filters, basically what you're learning on the first layer of the convnet, also has 3 channels. So you can just take them and plot them as images. And it's a nice way to quickly debug the first layer. You can't do that for other layers because they have hundreds of channels. And you no idea how you could plot that in image form, right? So what you see here is 7x7 filters. Each square is a 7x7 that's running over our input images and and it will be activated when the image is similar to the filter. So you see, say maybe we've got like a blue filter. If the image is blue, every time that filter hits something blue, it'll fire a signal and be like, oh, it's blue. And then we can take that as part of our classification. So basically here you see there's color filters. There's sort of color edge detecting filters in some cases, like this this red and pink one, where it's detecting boundaries between colors. And then we have these sort of black and white classic edge detectors that will be used for finding shape and that sort of thing. So it looks right. It's not noisy. It's another debugging technique just to check that nothing's going wrong. OK, let's go on to a bit more of a complicated technique that I don't really have an explanation for why it looks like it does. So what do we do here? Like I said, we can't plot the inside of the model past the first layer because it's too high dimension and there's no way to visualize it. So what we do instead is we take random images of Gaussian noise, put it into our network, look at the activation for the layer we're interested in. So say like the activation is 6. Then we optimize the image itself instead of the network to maximize that activation threshold. So that activation. So the idea is we're evolving images that excite certain neurons maximally. So they should somehow reveal what that neuron is looking for and what it's interested in. So on the left, this is the second layer. And you see, I don't know if you can see that well, but it's basically like little colored dots and patterns that it's trying to detect, which makes sense for that layer, because you don't, you're not necessarily looking to find structure at that layer. The idea is that each layer you'll compose these filters to build structure as you go higher and higher and higher. But then at the third layer, we have these very bizarre sort of like diffused, colorful clouds. And why? I don't really know. I'm not sure. On a traditional network, you expect to start finding structure at that point, like lines and curves and things like that. But we don't have it. So it's either the network's strange because we're using multiple images and multiple tasks, so maybe the filters come out differently, or my script is just not working, which is probably the more likely example. But it shows us something. OK, so I was talking about color before. Here's another nice one. So here, we've trained a model only on color, and we've done the same things we did before. So we project it into the representation into 2 dimensions and plot the results. And you can see that it's more or less clustering colors together correctly, so that's good. There's a few interesting things on here that highlight the problems we have with labeling color. So you see in the middle, it's just sort of like a big weird blob of like browny, yellowy, greeny, gray. And if you look at this is actually confusion between a bunch of color labels we have, which is like khaki, beige, light green, yellow. And the problem is like the humans themselves have different interpretations of what these labels mean. So our model is very confused and doesn't really classify them together. For this, if we wanted to make this perfect, I think I would re-encode all these sort of colors as natural, which a lot of other retailers do, and so to get rid of this confusion about khaki and beige. Another interesting thing is in this far side, we have like a reddy, orangey blob, which is weird because we've got a massive red blob at the bottom, and surely that red should be with the main red if it's truly red. And if you look into this, what's actually happening is these colors are more like a corally, what's pink and orange? Coral, I guess coral's right, yeah. Sandra's nodding. Yeah, so it's more like a coral. So that's interesting. We don't have a coral label for colors. But the model has said, although you're calling these reds, from what I've learned, these are different from the other reds you're telling me. So it's a cool technique that we've actually found new labels that we should be using. And there's also a similar one in a different plot. We've got a similar one for teal, because teal is between green and blue. And we don't have a label for that. So some people say green, some people say blue. And the model's like, what's happening? OK, so that's color. OK, another cool thing we did with this model to try and improve color detection is we said, what about if we take the first layer and we just do 1-by-1 filters? So there's no spatial information at all. It's basically just learning a pixel value. And the idea here was we thought maybe if we had 1-by-1 filters, a limited number of them would effectively be quantizing the image colors before it goes into the network. You know, we're basically mapping it down to a lower dimensional color palette, but that color palette has been learned for our particular data set. So we thought this would be cool. And it does work. It improves accuracy like by 1 or 2%. And these are the filters that come out, so it's quite cool. I haven't actually looked at later layers with this model, but the theory is that perhaps these filters will then get composed together to detect new colors, and they'll mix together to detect colors we haven't seen yet, and so forth. Or multiple colors, or multiple detectors will all be used for green, multiple for red, and that sort of thing. And if you look at it, we've mostly got red, green, and blue, and I guess a little bit of yellow as well. But that works quite well. OK, so another technique we can do is Deep Dream. So you might have seen Deep Dream, where it's basically the same as the way that we get the filters out. We're evolving images to maximize activations. But instead of putting random noise in, we put an actual image in. So this one's trained on a model on color, and it does this. So what's interesting about this is it does seem to be quantizing the image into distinct colors. Like you see, it splits the sky up into blues. I think these weird green line things is the actual color that it thinks it is. So if this was a dress, the model would think it would be green, I think. OK, we can do the same with category. So category, I think, is shape. So here we have a white image, and on the side we have an image of a dress. So if we do the process on this only on shape, we get something like this. So what's interesting about this is like the noisy image just sort of goes all blobby. The empty image goes all blobby. The dress image does the same, but the shape of the dress stays. Can you see that? It's not being overwritten with blobs like in the noisy image. So I think in some way that's showing it is detecting the shape of a dress. And the model gets this right. It says it's a dress, so I presume it's something along those lines. Don't know what the blobs are, to be honest. It's a work in progress. And here's another one. This is color and category. If we put them together, oops, sorry. Is it going? Oh, there we go. So we put them together, and it sort of turns it into a blobby gray shape. And it gets color and category correct, so it is doing something correct, but it's hard to interpret. But it's, I don't know why it turns everything into sort of like ovals, like the shoes and the legs and the arms, but it's interesting. Okay, so last one. I just thought, let's do all our tasks on a landscape and see what happens. And you see, so what happens here is you sort of get a combination of color quantization and edge detection all at once. But again, it's very strange because I'll show you a normal deep dream from a standard object detection network. You get something like this, right? So it starts putting sort of dogs and guinea pigs and eyes everywhere. But my model definitely does not do that. It just sort of it kind of makes it this abstract painting. So again, this is just interesting. There's no interpretation of what's happening. Yeah, and another nice thing we did, my colleague Mache did something similar to this, and we're trying to transfer styles between dresses. So we take an empty dress and a dress with a pattern, we try and put the pattern on the empty dress. We're like, oh, this will be so cool. And all it managed to do was change all the buttons to eyes. So not that useful, really. Okay, so final bit. I've shown you the model, shown you inside. Sorry I can't offer more interpretation of what it's actually doing inside. So what can we do with this representation? So here's a product on list, a £500 sweater, hoodie, standard. And you see we have images and we have very noisy text. And the designers write things like, oh, this would be perfect on a sunny morning walking down the lane with your friends. And they do all these like fluffy descriptions. It's not factual. So the descriptions are very, very noisy, but they contain like nuggets of good stuff we want, right? Like they might say, it's made of leather, dry clean only, has raglan sleeves. We're like, that's amazing labeling that we'd like for our models. So the question is, how can we take this description, take the representation of the image that we've just learned, and somehow extract the knowledge from our description? So we do something like this. So this is a model of two parts. The first part on the left is basically word2vec. We've just re-implemented word2vec. So for each word in the description, we try and predict that word based on the words that surround it. And in this way, you build up a textual representation, and it understands things like morphological invariants. So like going and go are very similar, and it learns that, say, dress is similar to skirt, but it's not similar to hats and those sorts of things. So it's learning about the textual context of each word. And again, this is representation that we've been talking about. Then we mix that with another model called a triplet network, which Calvin will be talking about more later. And what a triplet network does is takes something, you have a positive and a negative, and it tries to move it towards the positive and away from the negative. So we estimate our representation from the text, then we take our image representation for the two images and try and move the text representation closer to the positive image representation and further away from the negative. Yeah, this is actually a terrible example because they're both coats. So it doesn't really, there's a whole like art around sampling the correct negatives, but here it would move away from the pink coat even though it is a coat. So in this manner, and then again, we have two losses, we mix them, optimize the network. So now we have a representation that has jointly embedded images and text in the same space, so we can do distances between images and text. So let me show you what happens with the word2vec. Here's a few word pairs. when I say lexical distance here, I mean edit distance, how far away are the words in terms of their characters. And semantic difference, I mean the cosine distance in the representation space we've just learned. So a couple of interesting things, flared and flare. They're very close in their word form, they're very close in their meaning. That makes sense. Opening and openings, they're very close in their spelling, but they're actually quite far apart in their meaning in our data. So I presume that's because they're used for different sorts of products. So maybe opening is used for trousers, like leg opening, and maybe openings is used for, say, button openings or something like that. So they're like, although they look the same, they're used in semantically distinct ways, and that's what learning these representations gets us. I think the most interesting one is loops and belt loops. So they're very far apart in terms of edit distance, like 5, but they're almost identical in the semantic space. So that's telling us that we never use the word loops outside the context of belt loops. You'd never use loops in another context in our fashion data. So you can start seeing we're getting power about what words matter and how they're related. So then if we take a product, take all the words in the description and rank them relative to the image representation, in theory, we should get free keyword extraction. And that's what we get. So here's a shirt from Ralph Lauren. And sorry, I'm playing with my mic. So we rank all the phrases. So we take biograms and things like that. And these are the most relevant for this product. So we get things like embroidered logo, button down, placket, point color, classic, slim fit. These are awesome labels that will make our models even better when we retrain. And they're totally free. Like, we haven't had to pay anyone to get these labels. We're using the descriptions of products as weak labeling and extracting the most important ones from that weak labeling. So finally, I just want to go back to the start. The most important things for me are composition and representation. And you can see here, with both these models, we've just like Legoed together existing bits of functionality to fit our domain. And in the second example, we even took a whole model and just put it into another model so that we could do keyword extraction. So it's all about this composition that gives us a lot of power and lets us move very quickly. And the other thing is representation. None of the stuff I'm doing here would be possible if we only had a model that could do predictions. It's only possible because we have a model that generates representations. Okay, so that's me. Straight after, my colleague Calvin will be speaking also on using this representation for other exciting things. And he's also going to talk about his sort of journey into deep learning and all the pitfalls and that sort of thing. Thanks.
Thanks, great talk. I have a question. How do you make your initial corpus to use for labeling the data?
So we have humans who label stuff for us. And basically, we have like this consensus process where we give them an image, wait, and multiple people will select labels, and we wait till they converge, and we sort of give each. I don't want to stop calling them humans. It seems like very like dehumanizing, but. Yeah, no, they're real people that we know. Yeah, and then so we sort of rank them, and we know which ones are good and which ones are bad, and have this consensus process. But there's still like definitely error rates around this labeling. But it's quite an expensive process. We're lucky we have it, but it's hard to do from new.
How large did the corpus need to be effective?
You mean like?
Because he didn't use. Can you repeat that one?
Yeah, sorry. So you said how large does the corpus need to be effective? The training data. Well, of course, with neural networks, the bigger the better. So we actually have about 60 million images, but I only use 4 million for this just because it's a pain to download them, basically, even from our own servers. But Calvin's working on getting more images for us. So basically, the more you get, the better. If you've got 10,000 images, then basically the model has so many parameters, it's just going to overfit immediately. It's just going to, you put 10,000 images, it's just going to, like, the decision boundary is just going to be like, and just perfectly outline the data and overfit. So you do need a lot of data because the data provides the regularization to make the problem hard. If you don't have that variance in input, the problem's too easy for the model and you won't get a good thing out. So more the merrier.
Uh, so you have multiple objectives in your first network that you presented.
Mm-hmm.
You have multiple objectives that you train at once by averaging. Have you tried, well, in literature, sometimes they either pick the most informative objective and train it first, and then they alternate the objective to something else, or they alternate throughout the process. They sample at the final layer and say, okay, I'm going to train this now randomly. Have you played around with this? Like?
No, I haven't played around. Oh, sorry. You didn't hear that? I'll repeat it. So we basically said we're averaging the losses in a multitask network, but could you either randomly pick one task at a time to backprop, or
what people usually do is that you pick the most informative objective. For example, in the classification of like a jacket, probably a jacket is more informative in terms of structure in the image rather than color. So you would like to pick up the structure first and then continue with your training with the later epochs with color, for example, or additional things that might be more detailed.
Right, I see. We did averaging just because it's basically the simplest approach to start with. But yeah, there's loads of cool. So we can do things like drop tasks as well once they've trained up and give more power to the other tasks. I mean, yeah, there's lots of things we can do, but we haven't played with any of it yet. But
okay,
I might have a go.
Hello. Sorry. Can you talk a little bit about why you felt you needed multiple images? That's the one bit of the story that I found a little bit strange, because it feels like you disrupt information by having multiple copies or multiple different images and then averaging them.
Yeah, so, I mean, there's two reasons for that. One is it's sort of, well, primarily because we want representations on a product level for a lot of our machine learning structure, right? So if we're doing something like recommendations, we don't want to recommend people images. We want to recommend them products.
Don't they get tied together by having common labels, though?
In what sense? You mean the images tied together with the products? Yeah, but I mean, for instance, with our old duplicates, we did it on an image basis, and you run into, we have like run into problems before by having an image-based representation instead of having it at the product level. But I've tested it without multiple images, and you actually get a lower accuracy over it. It's only little. I mean, probably if you did it on an image-based level, you wouldn't lose that much, to be honest. But it's like 1 or 2% accuracy, and it just makes deployment and integration into our machine learning architecture easy, basically. But I think you could do it on images, yeah. It wouldn't be so different. Sorry.
Do you think your model recognizes the presence of a human model? If yes, was it trained to do so? And if yes, is it useful to then discriminate other characteristics?
I mean, does it detect if there's a model in the image?
Yeah, and was it trained to do so? Because in principle, that's one thing you don't want to average across images. Some may have, some not.
Well, one of our tasks is also gender. So in a way, having the model's face is quite useful if we want to distinguish between the gender. And you saw in the example, it actually takes, when we're just dealing with category, it actually just fades the model out, and doesn't care about the model and just leaves the shape of the dress. So I think the important thing with these deep methods is that you don't want to do pre-processing. You just want to provide enough data and enough classification power for the model to learn whatever it needs to learn, and you don't want to enforce priors on it, essentially, if that makes sense.
Hey, again about multiple images.
Yeah.
When you said you averaged the vector representation, and you sort of gave an example a simple example where one component might be learning something's red or something like that. How do you kind of ensure that they line up between the independent networks, or does that kind of automatically happen or drop out?
No, that's a good question. So when we duplicate the network n times, we don't have new networks with new parameters. We have exactly the same network. It's basically the same as doing a for loop through the network 5 times, basically.
Got it, yep.
So they're exactly the same.
Cool.
How do you validate the output that you're getting? Is there human intervention? So you're scraping your information from various websites, then you're running through your machine learning process. Is there then a validation through a human bodies, and then you go to production, or
Yeah, sorry, I haven't been repeating questions, but he's asking how do we validate our data that we're scraping, essentially. So at the moment, all our scraped data goes through humans, and we develop models in order to aid those humans and replace bits of them, like bits of their job, not bits of them, that'd be weird. But so it's basically like human in the loop style, right? We have this, try and have this collaborative ecosystem of man and machine, and we try and take the best from both and combine them. But we have to have validation. The spiders actually return some.
So the machine is a helper.
Sorry.
The machine is helping the human.
Exactly, that's the idea. Yeah.
I think you mentioned it, but I'm not quite sure if I understood it correctly. You said before that you use 4 million images to train it on.
Yeah,
does that mean you
million.
have to manually hand label those 4 million, or how do you deal with that massive amount of images that you want to label before you train the model?
Well, we're lucky because we've been going for 6 years, and since the beginning, we've always had moderators labeling our products for the site. Because our retailers and our partners give us very inconsistent labels. One might call it blue, one might call it cerulean hyperwave, right? They use all this weird language. So since the beginning, we've had in-house moderators who are labeling for us. Oh, wow. So we have 60 million labeled images now. So it's a nice resource to have as a data scientist, yeah. So it doesn't cost us now.
Thank you for the talk. You mentioned about a lot of problems related to the labeling of colors. Do you really need colors as labels instead of just using colors are in a continuous space? So can't you use just vectors for them or as representation?
Sorry, what was it?
Wouldn't it be possible to just trying to get a main color which is a vector and not a color label instead to avoid some of the problems?
Okay, right, yeah. I've got another presentation on color. And we did play about with that as well. Like, instead of getting labels, why don't we just get RGB values, right? And rank, or something along those lines, or lab values. And we did actually try that out, but there's a few problems. Like, say, for example, users want color labels because that's like the fashion norm. When you're on a high-end fashion site, it's always color name filter. So if we showed them like a Photoshop style like color spectrum, that might be a bit confusing. And the other thing is, like, even if you have color values, it's really hard to map those to names because there's nothing in the spectrum of light that suggests it should be segmented into labels, right? It's just a continuum. So the labeling of these intervals is an entirely human thing, and it's actually quite hard for a computer to understand why this is gray and why this is beige. It's like, do you see what I mean? So like the relationship between the colors and the labels is quite complicated to automate, but there's definitely been talk of trying to use RGB values instead of explicit labels.
Maybe one last question regarding the color.
Mm-hmm.
What do you do if the images are not color corrected? Or do you color correct them before you process them? Because that would kind of screw the model up, I guess, right?
I don't actually know about the image pre-processing pipeline. I mean, we're lucky because the image is extremely high quality. We have maybe like 3,000 by 3,000 pixels by professional photographers in great lighting and that sort of stuff, because it's basically the fashions brand's branding, the quality of their images. So we do have really nicely calibrated images, but it's true there could be inconsistencies between retailers, which is messing stuff up. I haven't looked at that, but might have a look.
Fortunately, we've run out of time, so thanks, Eddie.
Thanks.